everybody. It's Professor McDonald answering your questions on a Monday evening. Here you can see the first question is with a frequency distribution table of test scores on a 10-point quiz with the frequencies here on the right. And we've been asked to find the mean score for the test and the median score for the test. Now the way that this table works is it's showing you a summary of the test scores. So instead of just having one test score with a value of 3, the frequency here shows that we have 3 test scores that were equal to 3 points, and 3 test scores that were equal to 4 points, 1 test that was equal to 5 points, and so on. So you could list out all your test scores. So 3 points on 3 different tests, 4 points on 3 different tests, 5 points on 1 test, 6 points on 3 tests, 7 points on 3 tests, 8 points on 1 test, no tests with 9 points, and 10 points on 2 different tests. So now, altogether, I guess we could say, yeah, that's it. Altogether, how many do we have here? We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 test scores. So normally what you would do when you have all your data values lined out like this is you would add them all up and divide by how many you had. Now, do you actually have to list this out to get this done? No, you don't, because you could use a little trick. Instead of listing everything so you can add them up, you can use the shortcut of repeated addition, which is called multiplication. So if your test scores are your x's and the frequency is represented by the letter f, you're going to make a working column called xf, meaning x times f. I'll give a little room here. And we're just going to multiply each x value, each test score, times how many of those tests there were. In Excel, it's really easy to copy that down, and then we'll take the sum, add all the products together, and now this total right here is the same total you would get if you added up all of the scores that we listed out here. Let me show you. So the sum of all these scores should come out to be 93, and it did. Also, instead of having to count how many you have, you can simply add up the sum of all the frequency counts. So there you see the 16 that I counted earlier. So the shortcut way of doing things is to do all your products, add them up, and add up all the frequencies. Now the estimated mean from this will be taking this sum divided by the sample size. So 93 divided by 16 gives us an estimated mean of 5.8. Now, how do you find the median? Well, the median is the middle score when you list all your values out in order, or it could be the average of the 2 middle scores if you have an even number of values like we do here. Since we have 16 values, half of 16 is 8. So if you count 1, 2, 3, 4, 5, 6, 7, 8, not sure I counted that right. 1, 2, 3, 4, 5, 6, 7, 8. Okay. So now the division between the lower 50% and the upper 50% would be right here between these two values. And if you average those, you're going to get 6, right? So I'll just show you here. The median would be the average of the two center values when they're laid out in order, 6. Now, do you have to lay them out to be able to find your median? No. All you need to do is realize that half of 16 is 8. So you're going to count the frequencies, add them up cumulatively. So 3 plus 3 is 6. 6 plus 1 is 7. 7 plus 3 is 11. Well, the 8th and ninth value were in this category, up 6 points. So that's how you could figure it out without having to do the extra work. So the answer is 6. A test score of 6 is the median. Here is the next question from my inbox. It says we are going to calculate the standard deviation for the following set of sample data. So now we're going to first calculate the mean. You know, that's a typo. Actually, I'm just realizing it should say population data because the formula down here is for the population standard deviation. So that's something that could be improved on. But looking at the formula, this is what we're going to be using here, which would assume that this is not a sample, but it's actually the entire population. And what we're going to do is we're going to calculate this formula. We're going to work it out, and we're going to do all the steps of this calculation. And so you're filling out the intermediate values as you go along. So the first thing you're going to need to do is calculate mu, or calculate the mean. The population mean has the Greek letter mu. So let's start by putting in our values, our data values, 10, 3, 7, 3, and 10. And while in many of these problems it's easy to just copy and paste the data, this particular one is faster to just type them in because you have such a small sample. And then we're going to calculate the mean so that we can then subtract the mean from each x value to fill in this set of spaces. So let's get the mean. We'll do it over here. We can use the average function in Excel, or you can just add them up and divide by how many you have, which here we have 5. So there you would get the mean, 6.6. And now we are going to subtract the mean from each of the x values. So x minus the mean, start with the first one, minus the mean of 6.6. Now you can be fancy and do an absolute reference where you put dollar signs in front of the column and cell and row references for this cell, so it will be pinned in place, and then copy it down like that. Or if that's too fancy for you, you can simply do equals x minus and then just type in the value 6.6 and copy that down. So now we have our differences. These are the deviations, how far each of these x values lies from the mean. Now we want to square that each of those because we want to make sure that when we add them up to average them, you know, the standard deviation is more or less an average of the distance from the mean. But because we have some negatives and some positives, if we add these up, they're going to cancel each other out. So we're going to make them positive by squaring them to the power of 2. So we start with the first deviation, raise it to the power of 2, and then copy that down. All right, so now we have something that we can add. So we go ahead and add that up. Now this right here, this total, that is your variance. Well, it's not quite your variance until you divide by n. 1, 2, 3, 4, 5. We have 5 values, so n is 5. And this is the part of it that would be different if it was for a sample, because you would be dividing by 1 fewer. So we would have divided by 4 if we were calculating the sample variance. But here we're calculating the population variance, so we'll divide by the total n. And just to make this a little more clean, let's say population mean and population variance. And so the only difference, like I said, is if it was a sample variance, then we would divide by still the same total, divided by 4 instead. So then the population standard deviation is the square root of the variance. And likewise, the sample standard deviation would be the square root of the sample variance. Okay, so these, I don't think we were asked for the variance, but just the standard deviation. So now let's enter all our answers in. So now we have for the deviations. In Excel, it's actually quite easy to copy and paste these over if you don't want to spend the time retyping everything and risk making typo errors. So I'm just doing Control C and then Control V on my keyboard. Control C, Control V, 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 and the total, and then the standard deviation for the population, and then it asks us to round to 2 decimal places. So we're going to round this to 3.14. And isn't that a beautiful thing? Look at all those lovely green check marks. And here is the next question from my inbox. It says, at the 0.01 significance level, does the data below show significant correlation? Okay, so what we need to do is use the significance level to decide if the linear correlation strength between the variables x and y is going to be strong enough at a significance level of 0.01. We'll be using the test for linear correlation table. And so the first thing we'll do, though, is we'll calculate the linear correlation coefficient r using the given data here. And then we'll look up a value in the table called the critical value, which we will use to make a comparison. All right, so here, all we have to do to get our big long name, the linear correlation coefficient. Whoops, coefficient. Right, so this is going to measure how much linear strength there is between our values. Now, before I do this, even though we weren't asked to, it somehow helps students to see how these values are correlated in a scatter plot. And I see quite a strong linear trend there. There is something else going on, like there's some squiggle to it, so there might be an underlying factor, but it's going to have a pretty good linear correlation coefficient. So I'm thinking it's going to be around 70% or maybe even 80%, maybe higher. So that's what our dots look like. Let's see what the actual correlation coefficient is for our data, our sample data. Now, values that you calculate using sample data are called statistics, right? And the statistic that we're using here is to do a linear correlation test. So we're going to call it a test statistic. And the type of test we're doing is linear correlation, so we're using R to represent the linear correlation coefficient. So let's calculate it using the correlation function in Excel. And then you must feed each formula, and it asks for certain things. First, it wants array 1. That would be all your x values, then comma, array 2, and that would be all your y values. Then you can press enter, and look at that. We have a 0.862 correlation coefficient on our data. And notice that it is negative since the data trend, the line that would fit this data most closely would be going downhill from left to right, so it should have a negative correlation. Now, even though it's negative, it's close to -1, which, or close to, let's say, if you thought of it like a percentage, it's fairly close to 100%. So that is a very strong linear correlation. But we want to make sure it's strong enough at a significance level of 0.01. So our critical value, which is the comparison value, also referred to as R from the table, at, I'll put that here with 0.01 significance, R from the table. Now we're going to look it up. What do we need to use the table here? We need the degrees of freedom, and of course the level of significance. Now we already know what our levels of significance is. Let me double check that. Was it 0.01? Yes, 0.01. All right, so 0.01 is here on the end, so we'll be looking in the last column for our comparison value, our critical value. And we also need to decide which row to look in by the degrees of freedom, which is equal to n minus 2. Now, n is the sample size, so look over here, how many x values or xy pairs did we have? And we had a total of 12 xy pairs. So the degrees of freedom would be 12 minus 2, right? So being that n is equal to 12, the degrees of freedom is equal to 12 minus 2, which is 10. So we want to look in the row with 10 degrees of freedom. So here you can see if I can highlight this. This is the row we want to be in. And we want to line it up with 0.01 significance. So here is our critical value. And even though there's no sign on it in this table, you match the sign. It's not going to let me paste that. Here, type it in 0.708, 0.708, and you give it the same sign as whatever your linear correlation test statistic has. So we'll make this negative. And then you judge which one of those is closer to, or I guess the easier way to say this is which one of those is farther away from 0, because 0 would represent no linear correlation. So let's draw a little picture here. We're going to have a, ooh, terrible at drawing straight lines on this slippery screen here. Ooh, that's my best here. So 0 in the center would be no linear correlation. And then if it's all the way at +1, that would be perfect positive correlation. And if it's all the way at -1, that would be perfect negative linear correlation. So where does our test statistic fall on here? It's negative 0.862, so that's right around here. And then let's look at where our critical value is. The critical value is negative 0.708, so that would actually be over here. So the critical value is what you have to meet or beat. In other words, you have to get farther away from 0 than that mark. And since our test statistic is closer to -1, there is significant linear correlation here. So that's our answer. We're just going to say yes, there is significant linear correlation for this set of paired data. And here's the next question. It says the box plot below shows salaries for CPAs and actuaries in a town. The CPAs seem to be making overall a lower salary than the actuaries. And then we're asked if a person is making the first quartile salary for a CPA, they are making less than what percentage of actuaries? So let's first locate the first quartile salary of a CPA. First quartile salary of a CPA is right here. So that lines up with $40,000 a year. So a person who makes $40,000 a year is making more than 25% of CPAs. Now, they are making less than what percentage of actuaries, though? So the actuaries, on the actuary scale, that would be the minimum. So if you're already at the minimum here, then all the actuaries are going to be making more than the CPAs in this quartile, right? All the CPAs in that quartile are making less than the actuary that makes the minimum salary for actuaries. So that's why we would say 100% is the answer here. So we're going to say 100% of actuaries, right? So a person who is making $40,000 a year is making more than 25% of the rest of the CPAs, while someone making that same salary is actually making less than all of the actuaries. Okay, 100%. And that was the last question in my Lumen Ohm inbox from my fully online students. So I will look forward to seeing you guys again. I don't actually see you, it's just me here recording videos, but hopefully you guys are watching them. And I'll be making another one on Thursday to answer any more questions that are submitted. And as always, you can get help from the SLC tutors and save your receipts for extra credit. And you can also visit me during office hours. Remember my office hours, there's a link on the course information page in Blackboard. But just so you know right now, I'll go ahead and remind you, Monday through Thursday, and we have from 12 noon to 1:30 p.m. and also from 6:30 to 7:30 p.m. on those same days. So I always love to meet students on Zoom. Hope you're having a great day. Bye now.